figure out what is the right answer here. A given B is something in terms of B given A. And what did people say? What are the things you got to do? 16 people said you put P of A on the top, and presumably they put P of B on the bottom. That is the right thing to do. So good job, everyone who did that. So P of A divided by P of B, that's the right answer. And that is going to let us do so-called Bayesian classification. So let's go with what we had last time. Last time we were working on this silly coin flip problem with the double-sided coin. And so Bayes' theorem, what does it do? Bayes' theorem lets you do, so it converts the probability of the data or the observation. Let's call it the observation. The observation given the class, you can convert that into the probability of the class given the observation. So that's how we're going to use Bayes' theorem. And the probability of the class given the observation, that's exactly what we want in classification, right? So you see something, you see some x value, and you want to say that is probably class 1 or not, or whatever class you're doing. And the point is that in practice, it's often easier to do. So this is, on the right here, is what we want, and this is easier to do. Easier to do. And Bayes' theorem lets you go between them. So that's what we're going to do. We're going to see a couple examples of how this works. Last class, I did it with this coin. So we had two types of coins. So the example from last class, we had two types of coin. We had the type heads, tails coin and the type heads, heads coin. Those were our classes. And the observation was heads or tails. So you flip it, you look at one side, you either see heads or tails. And we specifically said, if you see a heads, what is the chance that it's actually the heads tails coin? And we saw that that was 1/3 by Bayes' theorem. But in general, this is the kind of idea. And this is a perfect example where calculating the probability of a heads, given it's a type heads tails coin, or calculating the probability that it's heads, given it's a type heads heads coin, these are like super easy. Anybody could tell you these. So if you have a heads tails coin, what's the probability you see a heads? That's a half. If you have a heads heads coin, what's the probability you see a heads? It's 1. So these are easy, right? This is the easy part. So very often, if you know the class, the probability of the observation given the class is quite a bit easy to do. And the thing you want is, the harder thing that I think bamboozled a lot of people last class. What's the probability it's a type heads tails coin given it's a heads? We saw that was 1/3. That was last class. And that's harder, but that is the thing you want when you're doing classification. So that's the setup. We're going to see some examples. But any questions or comments about importing the knowledge from last week? Okay, so we're going to use Bayes' theorem. Let's see, where do I want to start here? Why don't we start? Let's start with the fun thing, which is the little applet. So here is the little applet, just to make things a little concrete, which I call my Bayesian discriminator. Let me turn off some of these things. No peeking, no cheating and looking at what I'm doing. Okay, so here is a little thing. I got two types of points. Let me make the points a little bigger. So I got observations are x values. So instead of seeing a heads or a tails, you see a number. Yeah.
Sir, I was asking that, is probability the only way to solve classification problem?
Well, I mean, we did it with logistic regression already, which was, again, using probability. Yeah. I think everything can be interpreted as a probability. You can also interpret it other ways, but everything can be interpreted as a probability. Yeah. That's a good philosophy question. Yeah, okay. So in this example, I have the observation as an x value, is one-dimensional. In real problems, of course, the observation is multi-dimensional, but just to get started, we're going to make it one-dimensional. And I have two classes. I have the orange class and the blue class, okay? Then the orange class is at y equals 1, and the blue class is at y equals 0. So you can think of either 0 or 1. And now we're going to try to set up these Bayesian things. And the question we have to answer is, how do we estimate for a given x value, what is the probability of that x value being a blue point, and what is the probability of that x value being an orange point? Because that is what the method is here, right? So we have to answer the easy part of the equation, which is, what is the probability of some observation given a class? So in my example 2, here are the observations. The observations are x values, x in, I don't know, you want to say minus infinity to infinity? Yeah, why don't we do that? So you see some x value, and we have two classes. We have the orange class, orange, and we have the blue class, blue. And we have 3 data points in each. So we have 3 examples, and 3 examples. And this is what the Bayes method does, is it converts, if we can figure out what is the probability of seeing some x value, or in this case it's going to be a probability density, but I'm just going to write it like this and be, I guess, a little cavalier about, technically it's a probability density. But I'm just going to write probability equals. Put equals in quotes if you're worried. Given it's orange equals question mark, we're going to put the probability x equals x. Given it's blue, if you have a method to answer this question, if you can answer this question, that's the quote easy part, then Bayes' theorem will answer the question that you actually want, which is, how do you classify? So that's what we're going to do. Let's brainstorm. Let's come up with a little list of ideas. And we'll put them here. Did I make a word cloud for this? I might have. Okay, so let me go to mathematize, and you guys tell me your ideas. So how are we going to come up with some methods to do this? And I just made it a word cloud, so you can type in anything you want. Give me some ideas. Okay, so think of, you're given these points, right? Oh boy. Okay, you're given those points. Where did they go? Oh man. Okay, we have a lot of windows to get through. So I'll draw the picture over here again, and I'll find it while you're thinking. So you have some orange points up here, and you have some blue points up here, and I want you to think about, how would you find, for a given x value, how would you find, so here's x equals, I don't know, 3. Calculate these probabilities based on the data. That's what you got to do. And let me give you like 2 minutes to brainstorm. There's a lot of different things. If you saw the videos, there's some specific ideas in the videos, but you can think about this problem like more generally, and there's a lot of different ways you can do it. So brainstorm, and then we'll go work on that. Okay. Okay, there's like 30 seconds left. I only have one answer. Who would like more time? Let me give you guys some more time. Okay, like 30 seconds left. If you have no idea, I guess you put it in, I don't know, but probably you've come up with something that's like half-baked. Put that in is even better. If you have some kind of idea about how you would go about this. All right, put in your final answers. A few people still have to put in something. But let's see what you said over here. I got 17, 18 answers. And let's see what you said. I'm gonna zoom out for the word cloud. Okay, this is my favorite. All right. Okay, so let me do a couple of these. I like some people put dashes. Apply Bayes' theorem. That is not what we're doing, right? So I think this is an important thing to understand, right? Bayes' theorem is like a machine that takes the sort of answer to the easy question, what is the probability of the observation given the class, and answers the classification question. So Bayes' theorem is a conversion from this question to that question, right? So that's what Bayes' theorem is going to do, and this is the classification question. And now I'm asking, how are we going to answer this question? So apply Bayes' theorem is like one step ahead of where we want to be. We want to answer the easy question, and when it's something like coins, it's all really easy, right? Like you give them the sides of the coins, like you just calculate it. But what happens when you have data? Okay, that's what we're doing. Same thing here. Linear discriminant analysis is if you come up with a specific type of answer to this question, and then you apply the Bayes' theorem, you will get something called linear discriminant analysis. Same with naive Bayes is also, I would say, the same kind of thing, or quadratic discriminant analysis. So let's see maybe what people said in more detail. No. Great. So LDA is like the whole pipeline of doing a specific thing. Discriminant, yeah. So all of these things, okay, these are great. These are all like, we're going to have a list of different ways to get the probabilities, and then if you apply the Bayes' theorem, then you will get these three things. But what are they? Let's see. Quadratic, log transform. Okay. Conditional probability. Maximum likelihood. Okay, this is one. Well, I'll write that down in a second. Let's write that down right now. Maximum likelihood. So one method is, quote, maximum likelihood. Maximum likelihood, which you've seen before. So I'm going to give you guys 1 minute. Where did we see it before? We saw maximum likelihood earlier in the course. Where was this before? Okay, I'm going to give you 1 second or 1 minute to remember where we saw maximum likelihood. And another one that was on there is KNN. I'm going to also give you, we also saw this before. These are two methods we saw before in the course that were answering different questions, but the like general idea can be used here. So I'm going to give you 1 minute to try to recall where was this used before, and then I will tell you the answer. Okay. So just think. Nothing to do here. Okay. Oh, that's not what I want. That's not what I want either. Okay. Okay. Oh, I pressed the wrong button. Okay. Let me try this. Okay. Maximum likelihood. Okay. Does anyone remember where did we see maximum likelihood?
When you were introducing logistic regression.
Yeah. So in logistic regression and even in linear regression, maximum likelihood was actually how we measured how good an answer is. So maximum likelihood tells you how to measure how good an answer is. And what we were measuring is we had some data and we had a formula and we were like, this gives us the error function, right? This tells us the square loss or the cross entropy loss. So given some particular answer, we can measure how good it is. And if you can measure how good an answer is, you can try to improve your answer. That was gradient descent. And that is how a lot of things work. In this situation, you can also apply maximum likelihood, right? So you have some points. If you have some guess of an answer, so you say like, I think the blue points, I think the probability function is this thing. Whatever guess you come up with, you can answer the question, what is the likelihood of the 3 sample points you saw, right? And maximum likelihood says make that as high as possible. So maximum likelihood is a very general way to improve things. I think this is like the #1 way people would solve this. And in particular, you have to make some parameters. So maximum likelihood, let me erase this KNN. I'll write that down a little bit lower. But if you choose parameters, choose some parameterized form, and then measure how likely the data is. Okay. So, and an example of this is choose a Gaussian, or a Gaussian if you're fancy. So have some mean and have some variance, mean and variance. And then so say that the probability, and again, this is actually probability density, but I'm going to put equals in quotes, given class, let's say orange, let's pretend that's a Gaussian, and we just find the best parameters according to maximum likelihood. The best params according to maximum likelihood. Okay, so this is actually an idea we've seen before. And again, you can measure the maximum likelihood because you have some list of points. You know the probability at those points. And then you do that. I guess this shouldn't be an equals. Maybe this should be a according to, which is this little tilde.
Sir,
Yeah.
sir, that's the Gaussian function or something?
Well, so what I'm saying is this is a Gaussian distribution. So it looks like this. Right? So this thing looks like that. And it has some formula. I could write down the formula, but it's a little bit long and nasty, and we don't need it. So, this has some formula, and make this according to that. So that's why it's not an equals, it's a little tilde. So that's one thing. Of course, you could pick anything you want. So people like to pick Gaussians. There's no special reason to pick Gaussians unless there's something special about your data that you think it should be Gaussian. So for example, if your data is coming from a sum of different things, right? If your data is a sum of a bunch of different observations, then it might be, by the central limit theorem, might be Gaussian. So that's why people like Gaussians. But you could pick anything you want. I don't know. What's some other distribution? Let's make one up. Let's say it's geometric with parameter p. Okay, and then you do maximum likelihood on the p value and find that. That might be a good one to do. You could do anything you want, and depending on your data, maybe you have some insight. You're like, I know it's geometric, I just have to find the parameter p. Then that would be a great method. But you can pick anything you want, and that is the maximum likelihood method for estimating the density. So in general, there's the important ingredients. There's parameters, there's this likelihood function, and you look at all the parameters and you make the likelihood as large as you can, and that's the best parameters. That's how linear and logistic regression worked as well. Okay. Questions or comments about that? So this is something we've done sort of already. You pick parameters, you maximize the likelihood. This is like classical statistics. Some people call this parametric statistics because you have parameters. On the other hand, there's something else, which is the KNN method. And actually, the K here is not needed. I'm going to call it the NN method, where NN stands for not neural network, but nearby neighbors. Nearby neighbors. And this is another method that we did in the course. We did a fair bit at the beginning, which is what you do is at any point x, you see how many nearby neighbors there are. So probability that x equals x, given the class is orange, or let's do blue. Class is blue. U is large if x is near other data points. Okay, and I'm going to show you this in a picture because I think the picture will tell 1,000 words here. Let's go to this thing, and let me turn on this thing. So when you are estimating a function, I call that the nearby neighbor or the k nearest neighbor. When you're estimating a density, it's called kernel density estimation. And I'm going to turn it on here. So here it is. Let's turn on just the blue for now. And here is some blob. I think you'll see exactly what's going on if I make this number really small. Let's make this number really small. Okay, so I have 6 points. And what is my density? It is 6 spikes that are on top of the 6 points. So my density function is these spike values. And the spike I chose has a characteristic with the 0.2. And actually, each of these spikes is itself a Gaussian density. So it's a mixture of Gaussians. And what I'm saying is the likelihood of any point is just like the sum of all these things. So like, what's the probability that x equals 2? Well, it's very close to 0 because there's no points near 2. What's the probability you're at 1.5? Well, that's quite high because look, there's a point at 1.5. And you have freedom. You can choose how big of a window you want to look in. So this is a very tiny window, so you can see them. But as you make the window a little bit wider, you see they kind of merge together. So here's some kind of intermediate width, where these three are just starting to merge together, those two are just starting to merge together. And like we said before, you want to find the Goldilocks zone where it's kind of actually representing the data. So maybe something like that. And now these 5 have all merged together into one big blob. This point over here is its own small blob. And that is a perfectly good estimate for the density. If you go too far the other way, you're going to also get garbage. Like if you make it really flat like this, then I'm just saying like all the points are spread out. That's probably not good either. So this is too big. This is too small. And just like we saw, you can make some notion of finding the just right zone. Maybe it's like that. So this is called kernel density estimation. And it's the nearby neighbor version of finding the probability density function given some data. Any questions or comments about how that works? So let me write down the formula because the formula is something we've seen before. So it's the sum over all points. And you have some function, some density function that depends on the difference of x to xi, where you sum over all the data points xi. And then to make sure that it all sums up to 1, you divide by the right normalizing constant. I'll just say C, where C makes it sum to 1. And if you pick a Gaussian, this is called Gaussian KDE. Example, Gaussian KDE, kernel density estimation. This is a really common technique, and that's when phi of xy is e to the minus x minus y squared, and usually there's a parameter sigma over sigma squared. But you can pick any function you want. You could do a window or anything you want. It's just a measure of how close 2 points are, and it leads to this nice picture. These little blobs, and you got to tune the sigma value to make it just right. Okay, so that's a nearby neighbor averaging situation. Okay.
Excuse me, sir.
Yeah.
So the kernel density estimation, the kernel are those only that we studied in SV.
So in the kernel density estimation, you have to pick the kernel, which means also picking like this thing. This thing is sometimes called the kernel. So you pick the shape of the kernel and the width of the kernel, and then once you have that, then you do this sum. Did that answer your question? What was your question?
Sir, I was asking that these are the same functions that we use in SVM while classifying.
I don't think it has anything to do with an SVM.
No, means this Gaussian.
Yes. This thing comes up everywhere, right? So this formula is the formula for the density of a Gaussian. This is the probability density of a Gaussian centered at x with variance sigma squared. What is the probability it's equal to y? Let me write it like this. Okay, and then I guess let me stick with probabilities and write equals in quotes instead for densities. So this comes up all over the place, right? This, if I had written the nasty formula over here, it would have been the same formula. You know, it comes up everywhere, but there's no reason you have to do this one. I think it's important to know there's nothing special about it. It's just any kind of kernel that you have. Yeah, that's a great point. Yeah, so this of course comes up everywhere as an example of a kernel, but there are many other kernels. Okay, great. Any other questions? Okay, so that's a method. And in fact, this is basically all the methods we're going to do. And if you put in different kinds of special things, you get different kinds of answers. So once you know this, you do Bayes' theorem, and that gives you the answer. So let's do it. So let's apply Bayes' theorem now. And actually, let me show you the picture of applying Bayes' theorem. Let me start with this one, because it's up here. So that's the blue. This is the orange. Let's turn on the orange and turn on the blue. So again, I just picked some kernel, and then I used kernel density estimation. Given these blue points and these orange points, please estimate what is the probability density of the blue and the orange distribution. And you see the blue distribution has these two kind of bumps over here. The orange has 3 bumps. It has a big bump over here because there's 3 points, and it has a small one here and a small one here from these points. But once you have estimated that, you can turn it into a classifier by applying Bayes' theorem. And what you will get is this. Boop. Okay, so let me turn off the other lines so that we can see them more clearly. Let me turn off this and turn off this. So now the orange line tells you, given an x value, what's the probability it's orange? The orange class. And you can see these points are 100% chance or close to 100% chance of being orange class. These points are almost 100% chance of being blue. And then in the middle, you have some weirdness going on, where you're saying, I think a point that is chosen here is very likely to be blue, and I think a point chosen over here is very likely to be orange, right? And it really is just the ratio, the weighted ratio of the blue to the orange area. So let's write down the formula, and you see how you get it, but hopefully you can see what the idea is. You convert from these density estimations into a probability of either class by using Bayes' theorem. And let's write it out. So the probability of some point x being class, let's say orange, given the x value, x equals x, by Bayes' theorem, this is the probability that x equals x given that it's orange. That is what we just figured out. And you have to multiply by the right things. And the thing you have to multiply by is the probability of orange divided by the probability of x equals x. Okay, that was what I made you guys do in the warm-up. Now here's the thing. The probability that x equals x, that can happen in one of two different ways. So now I'm going to apply something called the law of total probability to split this up into two parts. And there's the probability x equals x given that it's orange. Okay, actually, why don't I split it up? I'll do it in two steps. So it could be orange. So the probability it's x equals x and it's orange, plus the probability x equals x and it's blue. Okay. So there's two ways it could be x equals x. It could be either x equals x with orange or with blue. And each of those I can also write as a conditional probability. So it's the probability x equals x given that it's orange times the probability of orange. That's the top of Bayes' theorem. And you see the bottom is a very similar situation. It's the probability x equals x given that it's orange times the probability of orange again, plus the probability x equals x given that it's blue times the probability that it's blue. Okay, and that's a very nice looking probability. It's the weighted average of these two things, right? You have these two probabilities, the probability given that it's orange and the probability given that it's blue, and you're doing this part divided by the sum of that part plus some other stuff. So it's kind of, you can see why it's between 0 and 1. Okay, and so this is the two estimates from before. This was the estimate from before. Estimate orange. This was estimate blue. And you do the weighted average of these two things. And that's what's going on over here. You might notice there's one parameter, P of orange. And that is up to you to choose. Sometimes this is called the prior probability, P of orange. This is the probability a point is orange if you don't know anything of a point being orange given no information. Right? So we're not given any x values at all. And so that's like saying, before you see the x value, what is the probability of it being orange? In this situation, I set that to 0.5. So I think I have that over here. I have the p-value, it's 0.5. So I'm saying if you give me a point, if I don't know anything about it, it's equally likely to be orange or blue. But in the Bayes' theorem, you can set this prior probability to anything you want. So maybe you know that most of the time an orange point will come in. So you know like 90% of the points are orange. Then maybe you want to set this all the way up to 0.9. And you see, when you do that, it changes the situation. I think P is actually corresponding to the blue class here. Yeah, okay, P is the blue class. So P equals 0.9 in the way I've written the formula. So I'm saying 90% of the points you get, you should think of, there are very likely 90% chance before you even see the x value is going to be blue. And you see the classifier changed to classify more things as blue, right? So now we need a lot of evidence before we classify something as orange. And you can make that even higher, maybe in the 99%. And now I'm saying like, look, really, it really has to be way over here for me to say it's orange. These points, even if you get a point over here, it's probably a blue point just because there's so many more blue points. And so that's a nice thing about these Bayesian things. You can incorporate this prior probability to make it do what you want. This is really important in like medical trials. So when they do like rare diseases, they say most people don't have this rare disease. So we set the prior probability to like 0.1, right? Maybe only 5% of the population has this rare disease. So if we see some like weird test result, we shouldn't automatically assume you have the rare disease. We should incorporate how much evidence does this thing give you that you have the rare disease. And so here it's the other way, where like most people are orange, and I'm not going to assume you have the rare disease unless there's a lot of evidence for it. So that's a nice thing of these Bayesian things. You can tune this based on what you know. So can tune this. Okay. So there you go. Any questions or comments so far? Yeah. Yeah.
Are we taking the p-value as a random guess or something?
So the p-value is like the fraction of the data that is one class or the other class when you don't look at the x values. So in this situation, I guess if you were going to say all of this data was generated in the same way, I would take it to be equal to, there's 4 orange points, wait no, there's 5 orange points and 6 blue points. So I would say based on the data set I have, it looks like 6 out of 11 of the time it's blue and 5 out of 11 time it's orange. So I would set it to, I guess in this situation, 6 out of 11. So that's how I would do it based on this data. Of course, in real life, maybe it's like, look, here are 5 healthy patients, and here are 6 patients that have the rare disease. The 6 rare people from the rare disease actually came from a population of 10,000 people. And so actually the p-value is like whatever it would be. So you can calculate the p-value based on something you know or based on the data, but it is something you set, and it's what is the chance of it being orange or blue without using the x value. That's what like the real interpretation. Great question. Any other questions or comments? Okay, so that one is something you haven't seen before, is doing this Bayesian classification with the KDE, the kernel density estimator, and I called it the kernel density Bayesian discriminator. Okay, let's do the other ones. So the one you saw in the video was this kind, where you choose a special function and you find the right parameters. And one of them was called the linear discriminator, the quote linear discriminator. And in that one, you just assume that each class is the same Gaussian thing with different means, but the same variance. So sigma squared, let's say overall. So you pick one sigma squared, and you can pick a different mean for each class. In our picture, in our little dopey picture, let me turn off the kernel density estimator and the kernel discriminator. Here is the Gaussian density estimator. So here's what they look like. So it's saying you find a blue peak and an orange peak, and there you go. You might notice the orange peak seems a little bit shifted to the left. It doesn't seem to be centered on the data very well. What do you think is going on there? I just remembered there's a point way over there. Okay, so actually I think this is pointing out if you're going to do something like a linear discriminator, when you find the parameters, this parameter is the mean of all the orange points. And the mean of all the orange points is affected by that outlier that was way over there, right? The method I just showed you before with the kernel density, that didn't care about that other point. The other point over there had almost no effect on what was going on, but now it really has pulling everything to the right. But in any case, so here are my 2 Gaussians. They have the same variance. So if you make the variance of one bigger or smaller, it changes the variance of the other. And then by taking the ratio, so using the same exact formula as we used before, which is this formula, right? So now I have a different formula for these. Before they were some like wonky average, and now they're those nice Gaussian formulas. But whatever they are, you do their ratio. So it's the same exact formula as before. You do their ratio. So here's G0, G1, and here is the ratio, G0 and G1. And it looks like this, right? So taking this e to the minus x squared formula and doing the ratio, you get that. And yeah, once again, you can play with the parameters, right? So nobody tells you what the thing should be. Oh, they always look like that. Oh, that's interesting. This looks kind of familiar. This function looks like something we've seen in the course, right? So this, obviously the orange is 1 minus the blue, but it looks like this nice thing where it's like flat, 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 and then it goes up, and then it's flat, 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 flat. That has a name. We saw that earlier. You tell me what it is in mathematics. What kind of shape / function does that linear discriminator remind you of? I'll give you 1 minute to recall. Okay, 10 more seconds. If you don't remember, you can say I don't remember. But I want to see how many people remember this shape. Okay, let's take a look at what people said. Do people remember the name of this special thing? Ooh, sigmoid in giant letters. Sigmoid is the right answer. So if you said sigmoid or sigmoid with a capital S, then you got it right. This is the sigmoid function. So for whatever reason, it turns out when you do this thing, all of the math we did turns into just the answer, sigmoid. That's the answer. And it's not a coincidence. Let me show you the math. It's actually very nice to see. So I'm going to show you the case. So the discriminator, this is the discriminator. And that's a function of the x value. We saw it was the probability of x given O divided by the probability of x given O plus the probability of x given blue. And here what I've done is I've set the p-value to a half. If you change it to something other than a half, then it won't affect things much. So I'm just going to do it as a half. And a half is nice because then it cancels out. It's on the top, it's on the bottom, it goes away. So I've just copied it over this formula. And I'm going to show you that anytime you have a probability like this, it's actually a sigmoid of something, right? What was sigmoid of x? Sigmoid of x was the formula e to the x over 1 plus e to the x, right? So I just got to tell you what x is, and this kind of thing should look kind of like that, right? What do I have to do to make this into that? Well, I have to make one of the factors on the bottom a 1, and then I have to do like the log of the other factor. So let's do that. I'm going to make one of the factors a 1 by just dividing the top and the bottom. So x given O divided by the probability of x given B, and then I'll have the probability of x given O divided by the probability x given B plus 1. So if you take this probability of x given B and you divide the top and the bottom, that's one thing you're allowed to do in math. When you have a fraction, you can divide the top and the bottom of the fraction and it's still equal. Now it's 1 plus something, and that is exactly the sigmoid of something. Let's do one more step. So this is the sigmoid of question mark, where question mark has the property that e to the question mark equals the probability of x given O divided by the probability x given B, right? So this thing equals the sigmoid of question mark, where e to the question mark is that thing. We have a name in math for solving this equation. It's called the logarithm. So what have I shown? Let's erase this. This equals the sigmoid of the log of the probability of x given O divided by the probability of x given B. Okay, there you go. So that's why it's a sigmoid. Anytime you do something with Bayesian, it's a sigmoid of the log, right? I haven't done anything. This is true always. But now in the case of assume the linear discriminator form, and now you really need the probability function. Here the probability of x given O is going to be this funny formula, 1 over square root of 2 pi sigma, let's put the sigma on the outside, and then you do e to the minus x minus mu O squared divided by sigma, like that. Okay, so that's the formula, and this is the special formula. This is exactly the bell-shaped curve for a Gaussian. And it's the same thing for the probability of x given B. Same kind of thing. Square root of 2 pi sigma e to the minus x minus mu B squared over sigma. Same kind of thing. The only thing that's different is the mean. Those are the two formulas. What happens if we divide them and take the log? Well, when you divide them, something nice happens. So the first nice thing that happens is they have the same factor in front. So this like stupid 1 over square root of 2 pi sigma, that goes away. They are canceled out. When you divide two things with exponentials, you are doing the difference inside the exponential. So this is now the exponential of minus x minus mu 0 squared over sigma. And then you do minus minus plus x minus mu b squared over sigma. So when you divide by this, you're subtracting whatever is in the exponential. division is subtracting inside the exponential. So this is a nice exponential. We want the log of it. That's even nicer. When you do the log, then this goes away, right? This goes away. So the log of the ratio of the probabilities is the difference of these two quadratic equations. And that is why this thing looks like the way it does is exactly the difference of two quadratic equations. I'm going to show you what that looks like in Desmos. So let me show you in Desmos, because I think I have it over here. Here's the densities. So the blue one, it's a quadratic equation. It's e to the minus x squared. You take the log, you just get minus x squared. The orange one, minus x squared. And they just have different centers, right? So these are the two formulas that I showed you over here. So minus x minus the mean squared divided by something, x minus the mean squared divided by something. Those are two quadratic equations, and here they are appearing. Let's take their difference. So d of x is the difference between these two things. Bam! D of x is a straight line. So these two things, they are both quadratic equations, and they are both quadratic equations with the same x squared term. So when you take the difference of two quadratic equations with the same x squared term, you get a line. So this thing is linear. This thing is linear. So this is the big observation. This is linear because the coefficient of x squared is the same. And in fact, if you calculate what it is, it's going to be, let's see. Well, okay, I don't even want to calculate what it is. Well, okay, it's let's do it. X minus mu 0 times 2 plus mu 0 squared, the minus. Okay, that's with the minus as well. Plus 2 x minus mu b. Oh, I think I want times. Okay, times plus mu b squared. And I think it turns into the straight line x minus mu 0 plus mu b divided by 2. So I'm going to skip some algebra. Twice this maybe. So it's a line which is 0 exactly at mu 0 over mu b. And I factored out, I think I factored out a 1 over sigma out of everything. Let me put that 1 over sigma back. So it's a line, and it goes through the exact midpoint of the two means. So here's the two things. The 0 of this is in the exact midpoint. Look, you can see that. They touch exactly at the midpoint between these two things. There's the exact midpoint. And so this is why this thing is called the linear. Why is it called the linear discriminator? It's because this line is a straight line. It's linear. You got these two quadratic equations. You subtract them, the linear discriminator. And it all comes out of the algebra. I think a better name would have been same variance Gaussians or something. So you have to do a lot of algebra to get to see the line. But there's the line. And that is why it's a perfect sigmoid. It's a sigmoid just applying this green line to it. One more thing I can show you is that if you change the variance, remember we were playing with the variance before, that was called R, you can make it wider or you can make it more narrow, and that doesn't change where the line is, but it changes the slope of the line. If you make it very vertical, then you get a very like, right? Like there's a very small window where you're ambiguous. If you make it very big, then they have more overlap. Then you have this like smooth transition from orange to blue back and forth. But that's the linear estimator, or the linear discriminator. Okay, here, I'm going to put this on a little loop. Can I play it? No, I can't. Okay, okay, don't do that. All right, okay, I'll stop there. What do you guys think about that? Any questions or comments? That's the linear discriminator. The quadratic discriminator takes 1 second to describe. All it is instead of having one R value for both, you have two R values. So maybe I make the orange twice as big as the blue. So now the orange is twice as wide as the blue. When you take a quadratic equation and you subtract it from another quadratic equation, if they have different coefficients, you don't get a line, you get a quadratic equation, right? This is the typical thing that happens when you subtract two quadratic equations. And now, depending on how you make this thing, you'll get all sorts of funny stuff. In particular, look, there's like this weird region where you're like, I think everything over here is orange, I think everything over here is blue, and I think everything over there is orange. And that's because the oranges, you told me they're very spread out. So if I see a point way over here, it's way more likely to be an orange that was like really far away from its mean. The blues are unlikely to be far away from their mean. So that's why you get these weird shapes in the quadratic discriminators. So that's the only thing that changes. You still, everything else is the same. Difference of the log likelihoods, but now it's quadratic. Questions or comments? Yeah?
Did you get the equation for this green line?
You can get an equation for the green line, and it's like you can get an equation for this, you get an equation for that, you subtract them, and it's no longer a line. And so it's going to have a term that's like x squared 1 over sigma this times 1 over minus 1 over sigma that.
So it's like the green line will have like two coefficients, x and y.
Exactly. It's going to have, that's exactly right. So it's going to have an x squared coefficient that is the difference of the whatever you put as the variances for the two things. So again, it's up to you. How do you want to estimate the variance? You could just estimate the variance of these points. That's one way to do it. But yeah, maybe you know that the orange points are very spread out, right? You know that if you're in the orange class, for some reason, the x's are very unreliable. I don't know. But so you can put them in all sorts of different ways or estimate them from the data. But they will appear in the green if they're there. So that's why the linear one is nice. Let me do one last thing about discriminators before we move on to something completely different, which is the exact same picture, but in 3D. So here it is in 3D. Let me turn off the classifier for now. So here are two orange, the orange blob and the blue blob, but now it's in 3D. And you can move them around. So you move, I don't know, this one moves like that, or like that. So this is Desmos 3D. And look, this is the cool thing you can do with Desmos 3D. You spin it. Oh, yeah, there we go. All right, okay. So there's the orange and the blue distribution. And now the x values are, there's an x1 and an x2. But as soon as you estimate the density, you can turn on the classifier by that formula. And you can see it's like a sheet, right? Like it's a 3D sigmoid. Okay, that's spinning too fast even for me. Okay, we gotta slow down. So it's a 3D sheet. It's the sigmoid function again, but in 3D. So it's a linear function. In 3D is a hyperplane, or I guess in this case just a plane. And you have the sigmoid function that is just barely hitting 1 at the top there. And you can move it by changing the p-value, just like we did before, right? Change the p-value. Or you can also make it a quadratic estimator by changing the variances. Let's make the orange really wide again. So here the orange is wide. This is the 3D version of what we saw over here, right? Where it goes orange in most places, then there's like a little region where the orange probability is low and then it's blue, and then the orange goes back up. In 3 dimensions, you get these quadratic bowls. So there we go. So if you're near the peak of the blue, then we classify you as blue. But otherwise, we're going to classify you as orange, according to this bowl. Okay, and you can also do it. You can even do it with 3 distributions. So nobody's stopping you from adding a third green. Here's a funny green one that's not even, it's a Gaussian, but it has some weird correlation structure. And you can still turn on the classifier. Let me turn off this classifier and turn on these ones. So here's orange, blue, and green. Those are the classifiers just by doing the ratios of these things. So anytime, what's the moral of the story? Anytime you can estimate the probability density for each class, Bayes' theorem lets you turn it into a classifier by doing the right ratios, and you get that out of it. Okay. Any questions or comments about this one? In real life, of course, it is important to know how to do the multi-dimensional one, because this nice one-dimensional thing is really good for learning what's going on. When you apply it in real life, you have to do higher dimensional things. Real life data is always very high dimensional, not one-dimensional, unless your problem is very easy. So there is one last one you must know, which is the so-called naive Bayes. This is the so-called naive Bayes. And this is, again, just some assumption that is made. And what you do in naive Bayes, you assume all x's are independent given the class. Independent given, maybe I should say conditionally independent to warn you. They're not really independent. They're conditionally independent given the class. And what does independence mean? It means that if you ask what is the probability of some x value given the class, then you can calculate, let's say, the orange class. Then you can calculate the probability as a product of things. So this will factor into the product from I equals 1 to the dimension, and you'll have the probability that x equals xi given class O. Okay, so what this is saying is that you reduce the problem. If this is a high multidimensional problem, in general, this would be hard, high dimensions, high dimension. That might be very difficult. And this is the 1D case that we just did, the 1D case. We just did. And so the naive Bayes says, if you want to solve a hard problem in many dimensions, just solve a one-dimensional problem and do it a bunch of times in a row. So do it dimension times. Repeat dimension number of times. Okay, and once you have this, everything else proceeds exactly as normal. So the naive Bayes is a way of taking a hard, high-dimensional problem and turning it into D copies of a one-dimensional problem. And of course, it's not always true. Like this assumption that things are independent may or may not be true, but sometimes it works quite well. And one nice thing is it works nicely. It can combines numerical and categorical data nicely. Numerical and categorical nicely. So if your data set has some columns that are numerical and some that are categorical, you can still pretend they're independent and estimate them individually and then just multiply them. But otherwise, it's quite tricky to come up with a distribution that is, Gaussian over here, but some weird combination of Gaussians with the categories. So that's one of the other reasons to use it. This is an advantage. Okay, I think they talked about naive Bayes in the videos. All right. Any questions or comments about the naive Bayes? Naive Bayes is it's a good one to practice if you want to really do it by hand. I know there's packages that do it, but you can try it by hand and see that it really works. It's because it's so simple. Naive means easy. This word means easy. This is a fancy word for easy. I don't know why they didn't call it easy Bayes. That would have been a cooler name. Okay. All right. Any questions or comments about that one? Okay, we're going to move on into something that's still related to classification, but is a slightly different question. So we've seen a few different ways to do classification now. We've seen logistic regression, which is like directly estimating the probabilities according to the cross-entropy loss. We've seen these Bayesian methods, which are actually just like, please estimate the probability of x equals x given the class, then use Bayes' theorem to invert it. But now we're going to ask like a higher level question, is like, what are we actually trying to do anyway? And I came up with this little example problem over here. Let me make sure I say the right one. Okay, yeah. Exercise 4. Okay, so this is what I'm going to ask us. When we're classifying things, sometimes things are not symmetric. So up until now, we have been saying that you want to get the classes right? Obviously, it's better to classify, if something is really class 1, we classify it as class 1, that's good. If it's class 2, we classify it as class 2, that's good. But in real life, sometimes things are asymmetrical. And here is the most asymmetrical thing I can think of. So suppose you are a shepherd, and you are trying to identify whether or not we are being attacked by a wolf, okay? So you're like a shepherd, you're in the mountains, you have all your sheep around you, and there's like a fuzzy blob like in the distance. And you have to decide, do we think it's a wolf or not? Have you guys heard the story about the boy who cried wolf? People are nodding. Yeah. Put your hand up if you have heard it. Okay, good. Last year, almost nobody had heard it. Maybe they didn't want to put their hand up. I should have asked. Okay. But in this situation, things are very asymmetrical. So you see something in the distance, and you have to decide, is it a wolf or not a wolf? Okay? So wolf we count as positive, and no wolf we say is negative. Okay? And a true positive means there really is a wolf, and we said wolf. So that's like we correctly identified that a wolf is attacking us. In this situation, what is the outcome? We are a hero. We ring the bell, the townspeople come and save us, and they're like, oh my god, you're so brave, you fought off the wolf. Amazing, okay? On the other hand, a true negative, if there is no wolf, and we say no wolf, and then everybody is fine. So that's great. That means we got it right. But now what I want to point out is there's a big difference between a false negative and a false positive. They are, in this situation, they are very different. In a false negative, that means the real answer was a false negative means, yeah, we got it wrong. So we were wrong and we said it was negative. So there really was a wolf, but we were like, it's just a black sheep or something. Then the wolf comes and eats all our sheep. That's really sad. Here's another situation, a false positive. So there really is no wolf, but we said wolf. So positive because we said wolf, false because we got it wrong, right? So we said it was a wolf, but there really is no wolf. And in this situation, everybody comes and they're grumpy at us. They're like, hey, you woke me up when I was taking a nap, and now I'm here and there's no wolf. What the hell? So those two situations are very different. And the question for you is, what should we do? What should we do? And I have 3 options. Which is worse? I said, which is worse? So your options are false positive is worse, and we should make that rate as small as possible. False negative is worse, and we should make that as small as possible. Or, if you want, you can balance them. You should balance them. So think about these 3 options. Pick your favorite. I'll give you 1 minute to think about it, and we'll see what people think. And I can bring up this little matrix over here. Yeah. The which is just for this? That's right, yeah. So when it says false positive is worse, I mean in this. Okay, put in your answers. Okay, so is false negative worse or false positive worse? There was a really good question, which is, when I say false positive is worse, do I mean a false positive is always worse, or do I mean in this particular case? And of course, a false positive for one person might be a false negative for another person. Like we defined wolf is positive and no wolf is negative, but like you could have easily said no wolf is positive because that's positive news. I don't know, whatever you want. Like you can flip these and then everything will flip. So what is a false positive really depends on what you count as positive, right? So a false positive to one person might be a false negative to another person. You have to fix what you mean and then they have meaning. And so like when somebody asks you which is worse, they must always mean in this particular case, right? There's the false negative on its own is meaningless. False negative in this case, that is what means something. Let's see what you guys said. Reveal submission counts. Okay, where is it? I have to zoom out or something. It's over here. Okay. 14 people said false negative is worse, and you should make the false negative rate as small as possible. 5 people said you should balance it. Nobody said false positive is worse. Yeah, I agree with that. False positive does not seem as bad. This is one of those situations. The vote was 14-5, and the correct answer is 5. The 5 people got it right. You need to balance them. Why is that? There's something, it really seems intuitive that this should be the right answer. And I agree a false negative is worse than a false positive. But there is a sinister mathematical mistake hiding in this statement. And I'll give you 1 more minute to chat with your neighbors. Why did most people get this wrong? They missed some simple thing. So I'm going to give you 1 more minute. Find the simple thing that most of you got bamboozled by. This is the wrong answer. This is the right answer. Okay, time's up. So who wants to tell me, maybe somebody who picked this and now realizes the error of their ways, what is the wrong thing in this? Why is this wrong? Why can't you just say, make the false negative rate as small as possible? So here's the little matrix. Right. Okay. Make sure that it never. So the false negative rate would making that as small as possible is saying never get in this situation where there is a wolf and the villagers don't come. Right. That's what we're saying. We never want that to happen. We want to be 100% sure that the wolf will never arrive and the villagers will not be there. How do you make sure that you never are in a situation where the villagers are not there? Yeah.
Positive all the time.
Yeah, you always say there's a wolf. You're like, hey, villagers, come on over. Just be here all the time with me. That's what happened in the story, right? The villagers will get pissed off if you do that. And then they won't come when you do need them. So the easy way to make the false negative rate 0 is just always declare everything you see as a wolf. Like that leaf wolf, that like bush wolf. Just always say wolf. Then you will never ever be in the situation where you said no wolf, right? Because you are always saying wolf. You just never do that. Just always say wolf. Right? This seems like a good plan, but it's actually a terrible idea, and that's what happened in the story, right? The villagers will get pissed off, and then they will not come when there really is a wolf. So even though it seems like the false negative rate is a lot less bad than the false negative is a lot worse than the false positive, it's not like infinitely worse, right? There is an amount of which you would rather accept one false negative for like a million false positives, right? It's not infinity false positives. And you need to balance them according to what that is. So the correct answer in classification, always, no matter what, no matter how imbalanced it seems, is always some kind of balance, right? You need to do some kind of balance. The balance might be very extreme. Maybe we want to have one false negative for every million false positives, but there is a balance, and it's not infinity. I think this is a very important lesson. A lot of people fall into this trap. And once again, you can always make these rates 0 or 1 by just doing the really stupid thing of always saying wolf or always saying no wolf. So if somebody says like, I can classify whether or not email is spam and I'll never misclassify a spam message as not spam, that's not impressive. Anybody can do that, right? So having a 0 error rate on false negatives or having a 0 error rate on false positives on their own is not impressive, because you can do the obvious thing. So I got this thing from this course over here, and in the last year they have changed it. It's no longer wolf and no wolf. But they added this beautiful little applet. So their definition here is spam and not spam. So they're saying you get an email, some emails are spam, some emails are not spam. So you have two types of things. So there's the true positive, it's a spam email that you classify as spam. A true negative is a not spam email correctly classified as not spam. Not spam is sometimes called ham. Okay, anyway. Then there's two kinds of mistakes you can make, right? You can either let through a spam email. That's when a spam email is misclassified as not spam. That's a false negative. That means somebody in their inbox gets a spam message. Or you can get a false positive. A not spam email is misclassified as spam. That's when somebody tries to send you a message, but you don't get the message because it went to your spam inbox, right? And these are, again, kind of asymmetrical. And it's not true that one is infinitely worse than the other. You have to balance them. And the beautiful thing Google has done for us is they have drawn this little interactive graph of classifying things. So you can imagine, you can take an email and on a scale of 0 to 1, identify how spammy it is, but then it's up to you to decide. Above a certain threshold, we don't let it in the inbox, and below a certain threshold, we do let it in the inbox. So imagine the x-axis is how spammy an email is, and if you make your threshold 0.5, you're saying everything on that side I will classify as spam. Actually, why don't I, to make it really crystal clear, why don't I do it like this? 0.53. So anything more spammy than this, I classify as spam. Anything less spammy than this, I classify as not spam. And you can see I'm making errors both ways, right? So the orange things, these are good emails. There are 5 emails that didn't get through. Let's dismiss this. Okay. Cool. Okay, so there were 5 emails that were nice emails, but I classified them as spam. There were also like 10 emails that were actually spam that I also let through. So by setting the thing here, then I've made those errors. I can change this. I can be really strict and only let through messages that are like only a little spam. If you include the words "you won't believe" in your email message to me, straight to spam, right? So in this situation, I'm making different kinds of mistakes. If you do this, you say everything is spam, then of course your error rate is 0 on one side, but the other type of error you make is a lot. And so where is the optimal thing? It depends on how bad a spam message is versus not. So you have to decide how to balance these things. The thing that you should know is this ROC curve, which should be here. If I zoom out a little bit more, where's the ROC curve? Hello? But there was an ROC curve. Where is the ROC curve? Let me try refreshing. Maybe I'm just a crazy person and I have to choose. Huh? Okay, well now it's completely gone.
So there is ROC code.
Where is it?
Left.
This? Okay. Oh yeah, okay, here. They're talking about it. Okay, here it is. So here, as you change the threshold, you cover this whole ROC curve. So here is extreme, classify everything as not spam. When you classify everything as not spam, your false positive rate is 0, but your true positive rate is also 0. And here is the other extreme, which is classify everything, no matter what, as spam, then your false positive rate is 100%, and your true positive rate is 100%. And this ROC curve, which was in your video, and I think they also described, is kind of all the possibilities in between. So as you change this from one side to the other side, you go through all the different possibilities. And in general, what you want to do depends on the problem. So if it's like wolves versus villagers being pissed off, maybe you want it to be like that. Like you really want to make sure that you really prioritize not getting eaten by the wolf. But sometimes you will get eaten by the wolf, and you have to do that. But in general, this ROC curve is like all the possible ways you could do it, and people use the metric area under the ROC curve as a thing. So they take the area of this curve, and that is like how good your classifier is. So the area under the ROC curve is the metric people use. Okay, this website from Google is significantly improved from last year. So last year it did not have any of these things, but now it has some really nice stuff. So I'm going to send this around. And I might keep an eye on the, I'll send an announcement, but I will probably change some of the readings you have to do to be from this nice interactive website instead of not. And they also have, they have this imbalanced case where things are a little funny. You'll have the project 2 has this kind of imbalanced data set in it where you have to do this kind of stuff and calculate the ROC curve. So this is a great example to learn. Any questions or comments about this ROC curve? I will send this around for you guys to look at as well. Okay, the very last thing I will do then is just give you guys some comments, general comments about the Project 1 drafts. So as you know, the Project 1 draft, you have to do your peer review by tonight. So please make sure you do the peer review and submit it. I have done almost all of them. I think I have like 6 or 7 students left to go through. Here are the main things I'm seeing that you can improve. So some people are, especially you will know if you're this person, if you don't have a great score, they are chronically underfitting. So they're trying to do overfitting and underfitting, but everything is underfitting. And those people, you'll notice that they don't have very high leaderboard scores. So it's very achievable to get to like 25,000. So that should be your goal. Try to get in this range, 20,000 to 25,000. And a significant way this happens is they don't use enough features. So if you're too picky about your features, you're saying, oh, the data in this column is bad, and you delete it. If you do that too often, you will just never get a really good score as you've thrown away too much data. So if you do that, try to do more features. Related to that is ordinal versus categorical encoding. So I think I talked about this in class a bit. If you prescribe the order, so you say poor is 1, excellent is 2, or whatever, that is not as flexible as giving it categories. So saying, is it a score 1, is it a score 2? That can give the model more flexibility to work with. And the problem is it might overfit, but if you're in this chronic underfitting, you probably want to use more categorical and less ordinal. So watch out for that. If you're doing a lot of ordinal stuff, is it necessarily true that the thing that you said is a 5 is twice as good as the thing you said is a 2.5? So make sure of that. There's 2 problems with kind of explaining, so people are not putting in enough details. I want to show you what some of the projects from last year looked like. So these are projects that got good grades, and they had a really nice table of contents. Like if you look at the table of contents, it's so easy to read because they have these nice subsections and sub-subsections where they do everything. So here I'm looking at the data set. Here I'm looking at the training data, and here are some different things I'm looking at. This is a little bit zoomed in, but hopefully you get the idea. So they remove outliers. Then they, here they did some nice things. And look, everything is like a nice text, exactly what I'm doing. I can see it's very easy to navigate. Lots of nice words. The executive summary is nicely laid out, right? It's got sections and subsections, even in the executive summary over here. So a lot of people just have like a blob of stuff, and it's hard to find exactly what you're looking for. So you should try to add in sections and subsections to make things work nicely. Another thing you can do is add plots. So people are sometimes describing things in words, like they're telling me this picture. They're like, first the picture goes up, then the picture goes down. I'm like, just include the picture. Like, it's a lot easier to tell me about the picture if I can see the picture. So that's something to watch out for. The TA told me that some people are having problems with data imputation. So like they're putting in like if the average square footage is not there, they put it in as 0. That's probably not right. So sometimes you want to put in 0. Sometimes you want to put in the mean. Sometimes you want to do the median. You got to think about it from a case-to-case basis. So watch out for that. Last but not least, if you're sort of stuck and like aren't getting good performance, the easiest thing to do is forward feature selection. So people who are doing forward feature selection are doing quite well. If you're doing something more fancy and complicated, you might want to consider switching to forward feature selection if it's not working. Some people it's working, that's fine. And very last thing, I tried to warn you guys, but everybody did this anyway. Make sure you use the entire data set for your final model. So you do a train test split. Don't use that as your final model. Use the train test split to figure out what to do, and then do the entire data set on the final model. Okay, yeah.
Sir, we have to include executive summary in the code or the PDF summary?
The executive summary is only in the PDF. Last year, it was not in the PDF. This year, it's in the PDF only. That's a good observation of what changed between last year and this year. Yeah?
Also, you were explaining in the